Welcome back to Management 670 Business Analytics. And today I want to talk about discrete distributions, how they differ from continuous distributions. Let's get started. The outcomes of an experiment are numbers, and they fall into two types of random variables. There are discrete and then continuous random variables. Discrete random variables have a limited number and known amount of outcomes and have a corresponding probability for each one of those outcomes, while continuous random variables can be any number and have to be talked about within intervals or as a collection of intervals. Discrete random variables can be infinite, but they have to be in a sequence that is known, like all positive integers starting at 0 and going on for infinity. Here are some examples of discrete random variables. Let's say you take 100 sales calls and you record the number of successes you've had or making a sale. So the possible values from that experiment would be 0 if you had 0 out of 100, or if you were successful every time, that would have an outcome of 100. There are a limited number of outcomes here, and if we knew the probabilities, we could calculate exactly what those are. What if we operate a restaurant for just a day and we record the number of visitors we have as customers? So while that is not capped at 100 like the previous experiment was, this one can go on forever. It's still a discrete distribution. It doesn't have to be a number that's gathered. It can be a category. So we can just record the gender of every customer that comes in to buy an automobile. A discrete probability has a definition where x is the outcome and f of x is the probability of getting that outcome x. Since it's a discrete probability distribution, we call that probability there, the f of x, the probability mass function. There are two conditions that have to be met for a probability mass function, and that is all of the probabilities of the outcomes have to be between 0 and 1, and all of the probabilities have to add up to 1. You have to have 100% coverage of all the outcomes that are possible for the experiment. Often, this is described with a table, a graph, or a series of equations. Let's take a look at an example. Let's say we are an investor and we believe that there are 4 scenarios of what the price of oil looks like in a year. We think maybe there's going to be a high demand, moderate demand, no growth at all in the market, or actually a moderate contraction. So we estimate that the price of the oil per barrel will be $78 for the high, $73 for the moderate, $63 for the no growth, and $50 if the market actually contracts a little bit. To be a discrete distribution, we have to know those prices. Those are our outcomes right here. And we have to know the corresponding probabilities. And those probabilities have to add up to 100%. So the table below shows that we believe that there's a 10% possibility that the demand for oil will be high in a year and the price of a barrel will go to $78. 50% for moderate, 25% for no growth, and a 50% chance that the market actually contracts a little bit. All of those probabilities are between 0 and 1, and the sum of them, as shown in the total, is 100%. So we have a discrete distribution with 4 different outcomes for the price of oil. Here's what the distribution would look like. We have the values down on the x-axis, probabilities on the left. We could talk about this distribution in a couple of ways that we've learned. We could talk about its location, variability, and also the covariance and correlation. So the expected value is the weighted average of all of the possible values. So 78, 73, 63, 50 are all the outcomes in the first column right there. The probability of having that outcome or that outcome occurring is listed in the next column, 10%, 50, 25, and 15. Fast sum just to make sure we are at 100. Again, we are. And so we take the product of that outcome and that probability and have a third column. So the $78, 10% chance, it contributes 7.8 towards the expected value. We do that for each one of the outcome and probability pairings, and we add those apart. We add those values together, and the sum is the expected value of the price of oil. Call this the weighted average. Since we are adding numbers that have been multiplied together, that's summing products, and that's why in Excel, as you can see at the bottom, that function is called sum product. In order to calculate the variance for this discrete distribution, we need the weighted average of the squared deviations from the mean. So the variance of x, or sigma squared, is the expectation of the outcomes x after you subtract the mean, square that. So again, we have our three columns here, the x, the probability of that outcome, and the product of those two. I then have another column here where it is the outcome, so in the very first row, the $78 minus the 67.55. We square that to clear out any negative numbers. I then multiply that value by the probability, in this case 0.1, and now I have the contribution towards the variance of the random variable. I sum that last column, I get to 77.148. That is the variance of the distribution of oil next year. In Excel, we use the VAR variance function. And then there is a trick in Excel to do many calculations at once called an array, and that's Control-Shift-Enter. Note that the expected return does not imply that we are likely to get $67.55. In fact, it's impossible. It's not one of the four outcomes that can be there. It's just the central tendency of the distribution. If we set this up as an experiment and run it many times, or have many trials, then the price of oil will be different each time. If we took the average of all of those prices of oil, that would be the expected value. The standard deviation, along with the variance, also comes into play. Covariance is the linear measurement between two random variables. We write it like this, COV, x comma y, so the covariance of the two random variables x and y. We take the expectation of the x outcome, subtract off its expectation, multiply that by the outcome y minus its expectation, and we add all those together. We then multiply the probabilities, those joint probabilities of x and y, to get the covariance. The correlation coefficient is the covariance, but you then divide it by the product of the standard deviations of x and y. That makes it so we can have a relationship, or we can have a description, rather, of the two random variables between -1 and +1. Let's look at this example right here. We'll say x can take on only 3 outcomes, 2, 3, and 4, and y can only take on 3 outcomes, 10, 11, and 12. The table lists the joint probabilities. So, for instance, there's a 24% chance that y is 10, the same time that x is 2. We can calculate on our own. The mean of x is 2.8, and the mean of y is 10.97. So this is our contingency table. At the very last row, we have the marginal probabilities of x. That last column, we have the marginal probabilities of y. In the table below, we have the covariance table. So the intersection between y being 10 and x being 2 is 0.18624. That comes from taking the y value of 10, subtracting the expectation of y from that, multiplying that by 2, since that's the outcome of x, subtract that expectation of x, which is 2.8, and then multiply that probability, that joint probability of 0.24. And that's what ends up in that cell. As you can see, you can add all of these together, and in the end, in the very last row and column intersection, we have a covariance of 0.274. We then, on the next slide here, can calculate the correlation between x and y. So we take the covariance of x and y, which we've determined to be 0.274, and then divide that by the product of the standard deviations for x and y. So we have a 0.23 correlation between x and y. We would say that that's moderate, positively correlated. So in general, as x increases, so does y, and vice versa. On your own, you can verify that the variance of x is 0.56 and the variance of y is 0.7491. There are a couple of very handy properties of expectations and variance. Let's assume that x and y are random variables and they have constants, A and B. So the expectation of a constant A multiplied X plus B can be transformed into just A times the expectation that's known plus that constant B. If you add two expectations together and then multiply them by the constants A and B, then we have the second property there. We can split X and Y and pull out those constants A and B. If we multiply the two random variables together, that's when we have the product of the expectations X and Y plus that covariance of X and Y. Let's take a look at an example. Let's say the expected sale of a product is 50 units. The price is $10. So what's the expected revenue? Well, that is equivalent of saying the expectation of 10 times X. Since that 10 is a constant, it comes out. We just have 10 times the expectation of X, which was given to us in the question as 50. I can substitute 50 in for the expectation of X and say 10 times 50 is 500. Let's look at the next question, where Y is the production. We say with the expected production, Y is 50 units. The cost per unit is expected to be $9. We have a correlation of 0 between X and Y. So what's the total cost? That's equivalent of saying the expectation of 9 times Y, which is 9 times the expectation of Y. Substitute that 50 in now. 9 times 50 is 450. We'll use this second property below to answer what is the expected profit. What's the expectation of 10 times X minus 9 times Y? That's 10 times the expectation of X minus 9 times the expectation of Y. I then can calculate those values, come up with 500 minus 450. So my expected profit is $50. Now for variance. Let's assume X, Y, and Z are random variables again, and A, B, C are constants. The variance calculation is a little bit trickier because AX plus B is not A times X plus B. It's now A squared times the variance of X. We can add a constant, B, as much as we want, but it doesn't affect the variance at all. It has an influence over the expectation, but not the variance. Take the variance AX plus BY. Well, we take the A and the B out. We're allowed to split X and Y as long as we then add this covariant portion, 2AB, times the covariance of X and Y. So that property says it's A squared times the variance of X plus B squared times the variance of Y plus 2AB, whatever those constants are, multiplied by the covariance XY. We can bring in a third random variable Z, and notice that that grows. We have A squared and B squared and C squared with their corresponding random variable variances. And for each one of those combinations, we add another term, plus 2AB, and the covariance between the two random variables. Grows quickly as we add in more and more variables, and it gets really ugly. Let's look at an example. Let's say X and Y represent annual rates of return for two stocks. We think X is 12, Y is 15. We have some variance calculations there as well. The standard deviation of X is 20, so the variance is 20 squared. Just like the standard deviation is 25 for Y, and we square that for the variance. So what if we put 40% of our money that we want to invest into stock X, and therefore 60% in Y? What's the expected return of this investment? That's a simple enough calculation using the property from the previous couple slides, where it's the expectation of 0.4x plus 0.6y. So the portfolio itself is worth 13.8 by expectation. The risk is a little bit more complicated because we have to use the longer nonlinear calculation from the previous slide, but we will end up with a variance of 361. Take the square root of that for the standard deviation and get to 19. In fact, we can play with that proportion that we put into X and the complement goes into Y and come up with this table right here. So if I put 0 into X, that means I put everything into Y and get that distribution. Or if I put everything into X, then I get the expectation and variance of X there. But by playing with increments in between, I can make different portfolios that use a combination of X and Y. So there's my return column, my variance column, and the easily to digest standard deviation column right there. Graph on the right shows the expected return between the different proportions we put into X, but risk is non-linear and has a more interesting curvature than the straight line of the expected return. In fact, we can take a step farther and say that of the different possible portfolios, there is an efficient frontier. Some of the portfolios from the previous slide are inefficient or not efficient, meaning that they don't offer as high of a return given the amount of risk we're willing to assume. Follow my mouse here. Here's the risk that we are willing to take on, the standard deviation of 20. This green efficient portfolio right here roughly hits that 20, but offers a much higher expectation of 14. So why would you choose this portfolio when this one exists? This is clearly suboptimal compared to this choice right here. If you're willing to take on this amount of risk, then you should have this amount of return. We call these series of points, or these possible portfolios, the efficient frontier. What we made in the oil example was a customized discrete distribution, one that we picked and then had different probabilities for. A very common, popular discrete distribution is the binomial probability distribution. It's the one that measures the number of successes, however it's defined, over n trials, where n is some number. So we call those observations or trials. For example, if you test a batch of 5 products that come off a manufacturing line, then the number of defective items there is a binomial distribution. Or if all of the questions are independent for a 20-question quiz or test, then the number of questions answered correctly is a binomial distribution. Of the last 100 people to come into the store, the percentage or the number that made a purchase is also a binomial distribution. It's a binomial distribution if we have a sequence of identical trials. So out of all of the n trials, they need to be exactly the same. And there can only be 2 outcomes. Only success or failure. They can take on other names, but one of them has to be designated as success, and the other one has to be the failure. We call the probability of that success is P, and it doesn't change from trial to trial. And finally, those trials need to be independent. We have a series of independent trials that only have 2 outcomes, and the probability of the success outcome doesn't change. Takes on this probability function here, where the exclamation point in math means factorial. So n factorial means n times the integer below that, times the integer below that, until you get to 1. The n factorial divided by x factorial multiplied by n minus x factorial is the way you calculate the number of ways of obtaining x successes in n trials. N again is the number of trials, P is the probability of what's deemed a success. So that probability function is n factorial divided by x factorial, multiply it by n minus x first, and then you take the factorial of that. You take the probability P raised to the number of successful trials, x, multiplied by the opposite of a success, which is the failure, 1 minus P, and that's taken to the n minus x power there. The expected value of a binomial distribution, or mu, is n, the number of trials, times P, the probability of success. The variance of the distribution, whatever it happens to be, is calculated as n times P times 1 minus P. So the number of trials times the probability of success times the probability of failure. Standard deviation is just the square root again of the variance. So in conclusion, discrete random variables are any distribution that has a limited number, a known set of outcomes, and their corresponding probabilities. The most common discrete distribution is the binomial, and we will compare this discrete distributions to the continuous distributions next time. Thank you.